Well, thank you very much for the supposedly nice words. Yeah, it's great to be here. Thanks for the invitation. It's really it's my first time in Korea, and of course I hope to come back many times. Okay, now this lecture is going to be about mathematical problems in quantum mechanics. So I don't really know how familiar you are with quantum mechanics. So just to gauge the level, I assume that you are just not familiar with quantum mechanics, and I'll try to sort of bring you up to the level that is needed for what I want to do. Okay, let me first say that actually this is based on joint work with two colleagues, and that is Thierry Paul he's now at École Polytechnique in Paris, and Christoph Spaber from Cambridge. Okay, and actually the manuscript is not completely ready yet, but should be out very soon. It should be in the archives in a couple of weeks or something. At least I hope so. Okay, quantum mechanics. The main equation of quantum mechanics is for sure the Schrodinger equation. So let me write the Schrodinger equation for you to begin with. So the Schrodinger equation is a linear partial differential equation for a complex valued function. Okay, so I have I, and I write the parameter epsilon, and I shall say in the sequel what this parameter epsilon is. So psi is the unknown function. Let me refer to it as the wave function. Here we have spatial derivatives on the right-hand side, and we are given a potential V of x, which constitutes the force under which, say, the quantistic particle that I observe moves in. Yeah? So think of V of x as a real valued potential, which of course is given. Then the unknown of the equation is a function of x and t, which, as Schrodinger referred to, is the wave function. I, of course, is the imaginary unit, square root of -1. And epsilon is a generally positive and very often small parameter, which we refer to as the so-called semi-classical parameter. In some sense, the size of epsilon tells you how far we are away from classical mechanics. The smaller epsilon is, in some sense, the closer we are to classical mechanics. And in fact, the transition for epsilon to 0 is something that I shall be concerned about in this lecture. Okay. Now you see you have here a first order time derivative, so you need one initial. Yeah, maybe I should say one more thing. Of course, x is the position variable, which for the purpose of this talk will be assumed to be d-dimensional. T is the time variable, which you may assume to be positive, but since this equation is perfectly time reversible, you can go in both directions. Doesn't really matter. Okay, so we are facing a first order partial differential equation. So we need one in, yes?
If you change t by minus t,
yes,
then the equation has changed.
Changed, yes, but then you have to take the conjugation. So if you change t to minus t, you get a -1 here, and then you conjugate the equation, you get the same equation back again. So in this sense, the Schrodinger equation is completely time reversible. Okay, so the initial datum is psi at time t equals 0, and I assume that it's just some given function, which I call psi I, and this may very well depend on epsilon. Okay, so this is the initial value problem for the Schrodinger equation. Okay. was actually written down for the first time by the Viennese physicist Erwin Schrödinger in the year, I think, 1926, more or less. Yeah. Okay, now this is a linear second order in space, first order in time, partial differential equation. If we assume that the potential V of x has nice properties, then there is really no problem with this equation. You can do your semi-group, actually it's group theory. You can prove that under good conditions on the operator, on the potential V, the Schrödinger equation generates a strongly continuous group of unitary operators, say on the space L2 of RD, and basically you're done with all the existent theory. Okay, but this is of course not what I want to discuss in this lecture. Let me maybe first of all say a few, maybe first of all make a few general remarks. What is this wave function that we compute? I mean, what you have to think of is this. You have to think of a physical situation in which you trace a particle which moves under the action of this potential field V. Okay, and we assume that the particle, of course, moves quantistically, so quantum effects are important. Yeah? So, but then what is the wave function psi? What you really want to compute, or what physicists want to compute, is so-called observables. Okay, now the question is, how do you compute observables out of the wave function? Well, to begin with, and a very important quantity is this quantity rho epsilon. And this is just the square of the modulus of the wave function. And why is this important? Well, this is actually called the position density. And that means basically that if you take the integral over rho epsilon, integrate with respect to x over some subset A in RD, this is just a probability that the particle which you are tracing is in the set A at time t. So in some sense, you could say that rho epsilon, is the most simple physical observable that you can write down. Another important physical observable is the so-called flux density. And the flux density in quantum mechanics is defined in this way. Let me write it in this form. I take the imaginary part of psi epsilon conjugate. By the way, I should say that in this lecture, by the dash, by the overbar, I denote complex conjugation. Okay. Then I have to multiply by epsilon gradient psi epsilon. Yeah, take the imaginary part. This is the flux density. And you can convince yourself easily that, assuming that psi satisfies the Schrodinger equation, sometimes I should be consistent in the notation. I write psi epsilon in order to denote the dependence of the function psi on the parameter epsilon. I'm sure during the lecture sometimes I will forget about the superscript epsilon, but it's the same thing anyway.
Why did you put epsilon in the flux density?
Yeah. Why did I put it here? That's a good question. And the answer is because I want the continuity equation to hold, which is this one. Okay. That's an immediate consequence of the Schrodinger equation. And in order to make this equation valid, I need this epsilon here. So basically then what you shall see hopefully later on is that if we do the right scaling, then for every derivative we need to put an epsilon up front. Okay, this is the continuity equation. Okay. Now there is another important observable, and that's the energy.
What do you mean?
An eraser?
Right. Over there.
Oh, okay. Big one. Okay, the energy. And the total energy is, well, is given by the total kinetic energy. I should write of xt squared dx plus the potential energy, which is, I can write rho epsilon of xt dx, and this has to be integrated, of course, over all space, and this, let me call it the energy. Okay, this is so here basically the first term is the total kinetic energy, and the second term is the total potential energy. So here you get the sum of both, and I should write a 1/2 here. Okay. Now you convince yourself easily that energy is conserved during the motion by the Schrodinger equation. So you have energy conservation. And actually I should have said that. You have another important conservation law which corresponds to the position density. Well, here I said that the integral of rho epsilon over the set A is the probability that the particle is in A at time t. So you really want the integral of rho epsilon over all space to be equal to 1, and this has to be maintained through the motion. And actually it really, so I mean, this is another conservation law. Oops. And I assume that this is equal to 1. Okay, then it's maintained through the motion. Basically, now you have all the conservation laws that we need. Okay, now this is the Schrodinger wave mechanics point of view of describing quantistic phenomena. There is other points of views. Okay, so let me just say this is Schrodinger's wave mechanics. There is other points of views to describe quantum mechanics, and another important one is Heisenberg's view of quantum mechanics. And I'm not going to speak about that here. Well, only in very little. A third one is the so-called Wigner approach. Yeah, well, Heisenberg, for those of you who don't know, Heisenberg was a German physicist. I think he got his Nobel Prize at the same time as Schrödinger got his, maybe in 1932. Then Wigner was, Eugene Wigner was a Hungarian physicist. He got this Nobel Prize sometime later, I think. Yeah. Well, maybe, yes. Very, very late, actually. Yeah. And for something sort of disconnected to his quantistic stuff, but I don't know exactly. Okay, there's another approach which is called Bohm's mechanics. And I shall speak about that later on. Yeah, maybe I should make one more remark on observables. So what are observables? Well, physically, observables are quantities that you can measure in the motion of a particle. So, I mean, classically, you have to think of, say, position, you have to think of velocity, of momentum, of energy, and so on. And as you see, in a quantistic framework, at least in Schrödinger's wave mechanics, all those quantities are defined probabilistically. Okay, and here you have sort of the 0th order observable, or the most simple observable, the position density. You have the next level up, which is the flux density. Well, the integrand that appears here is, of course, the energy density and so on. And in this way, you can define very general observables, infinitely many actually, and all of them are defined in the following way. You have to prescribe a function on phase space, which should be a real valued function. So you have to think of x as position space, you have to think of psi as velocity. Yeah? So this is a function which lives on phase space. I assume that this is a real valued function. Let me assume that it's a smooth function. And then I can define a general observable associated to the wave function psi epsilon in the following way. I write down, and now something a bit complicated. This is a pseudo differential operator. So basically what you have to think of that for the velocity variable, well, you have to replace the velocity variable by epsilon, by I epsilon times the gradient of respect to x, with respect to x. And you have to see this in the Fourier framework. Okay, I don't really want to define it precisely because we won't need it. And since this definition is not unique, we have to make it unique in a nice way. And that is the so-called while quantization. But I don't want to write down what it really is, because afterwards we don't really need it so much. All I want you to think about is that you can get that observables are essentially defined through self-adjoint operators. Okay, so you have to apply this to the wave function, and then you multiply this by the conjugate of the wave function, and you integrate over position space, and then what you get here is the average value of the observable A in the state psi epsilon. And of course there is infinitely many of those, since you can choose basically an arbitrary test function which defines your self-adjoint operator. Okay? Okay, so this is more or less a very, very fast run through Schrödinger's wave mechanics. Yeah? Now, let me go through Wigner's approach. Now, okay, Wigner's approach. Wigner's approach, well, Schrödinger's wave mechanics is completely based on position space. Okay, I have my position space, I define wave functions on position space, and then I go on from there. Wigner's approach is different. It's based on phase space. And basically phase space, as I say, what I mean is this space here. Okay. So basically what we do is this. We set up the so-called density operator. And I realize that this is a somewhat bad notation, because for rho, well, let me write R. Okay, and this is actually the so-called density matrix. But it's not yet the density operator. And this is also parameterized in T, and this is just defined as the tensor product of wave functions, where I take the first one and evaluate it at the position variable R, and I conjugate and I multiply by the second copy of it. I evaluate it at the position vector S. Well, you can do that, right? And this holds for Rs in R2D, and of course T in R. And you refer to this as the density matrix. Okay. Okay, now Wigner does something magic. Now what he does is he introduces a somewhat magical coordinate transform which basically operates on the R and S coordinates. So I do now a linear coordinate transformation from R and X, from R and S into, say, X and V. And don't think of V here as velocity. Always think of psi as velocity, and think of V as the dual, as the Fourier dual variable of velocity. Okay? And the coordinate transformation is the following. R is X plus epsilon half V, and S is X minus epsilon half V. Now don't ask me at this point why. No? I'd rather tell you what it does, okay, and why it is good for what we want to do. Okay, so that means I compute now R epsilon of X plus epsilon half V of X minus epsilon half V parameterized in T. That's just the density matrix after the coordinate transformation. If you don't like the R epsilon, think of it as the tensor product, and here you replace R by X plus epsilon half. You replace X by S by X minus epsilon half V. Yeah? Okay, and now Wigner does the next magic thing. He takes a Fourier transformation with respect to this incremental variable V. Okay, and this integral goes over RD. Yeah? And what comes out is, let me call it W epsilon, and this is certainly a function of X psi parameterized in T. And this is the so-called Wigner transform of the wave function psi epsilon at time t. Okay. And this Wigner transform is a phase space function. Yeah? And now, of course, the question that I have to ask myself is, assuming that the wave function satisfies the Schrodinger equation, what is the function that the Wigner transform satisfies? And that's actually a simple calculation. Actually, all you need to do is go through the steps of its definition and trace those steps through the Schrodinger equation and see what you come up with. Okay, but before I do this, let me tell you something else. I mean, all this seems extremely arbitrary at this point, right? Why am I doing this? Well, I mean, main reason why I'm doing this is because it does the right thing, as I want to show you now. Let me, for example, compute the position density. The position density is defined as the modulus of psi epsilon squared. Now you convince yourself that if you go through this algebra here, that you can compute the position density as the integral of the Wigner function with respect to velocity. That's just Fourier calculus. Okay, basically what you see that the position density is the trace of the density matrix. So this is when R is equal to S is equal to S is equal to X. So that means when this happens exactly when V is equal to 0. So by Fourier transform laws, you just get this. Well, this reminds you already of classical mechanics, right? Take a distribution function of particles in classical mechanics, integrate out, say, the velocity variable. Of course, what you get is the position density. Yeah? But the good things go on still. If I compute the first order moment, you convince yourself again through simple Fourier calculus that what comes out is the flux density. And that looks already very good, right? Okay. And the goodies still go on. If I compute this quantity, which is the second order total moment with respect to velocity, what comes out is just the kinetic energy, which is epsilon square half integral gradient psi epsilon of x d squared dx. Yeah?
And when you define the Wigner transform,
Mm-hmm.
so is it x plus epsilon over theta or v?
V. X plus epsilon half v, x minus epsilon half v.
Okay.
Sorry, that's a v, yeah, that's a v, and that's a v. Yeah, and then here you have the Fourier transform with respect to v.
Were there any intuition to take such a...
There's a lot of talk about what the intuition of this is. These algebraic questions. So I'd rather stay out of this. I don't have any. I mean, the only thing that you can say easily is that when you compute sort of dimensionally, yeah, then what you realize is that this variable is the dual of a velocity. The Fourier dual variable of a velocity. So it kind of makes sense to compute the Fourier transform. Yeah. Other than that, there's a lot of talk going on in the physics community on what the intuition of this is. I would have liked to ask Wigner, but unfortunately.
Looking at the 2 points where these points are separated by v.
Well, they're separated by epsilon times v.
Yeah, but if you scale it, it's just...
Yes. Yeah. I don't know. I'd rather stay out of this discussion. Okay, but just to continue here, in general, when you take an observable operator, an observable function A, you know, the one that we wrote down here, and when you integrate this against the Wigner function, yeah, what you get is precisely this expression here. Okay? After having appropriately defined the while quantization. Yeah, so this is really the integral of psi epsilon conjugate A of x epsilon d while transform psi epsilon dx. So basically this tells you that even if you don't really know exactly what this means, it tells you that if you take the Wigner function and integrate against an observable, you get physically the right thing. So this is already pretty surprising, right? Now you could say that, well, I mean, now I'm basically back to classical mechanics. But the answer is you are not. And the main reason is that in general, W epsilon is not non-negative on R2D. On the contrary, actually, if you look at numerical computations of of the Wigner function W epsilon, you realize that it changes sign extremely widely. Okay. Nevertheless, it makes sense. So, I mean, this means that this is not a classical distribution function. And this has actually inhibited for a long time its use in the applied mathematics and pure, and actually both in the applied and pure mathematics communities, because people used to say that this is useless. I mean, it has all these nice properties here, but I mean, it's not a distribution function, so what can I do with it? But I mean, I'll hope to tell you later on why this is a wrong point of view and why this is still an extremely useful object. Okay. Okay, so the important thing now is to write down the equation that the partial differential equation which is satisfied by this function, and let me just tell you that the equation looks like this. Well, and I'm sure that you have seen this term before. This is just the free streaming transport operator in classical mechanics on phase space. Well, I mean, that's not all to it. There is, unfortunately, I mean, this is like, probably you know the movie The Good, the Bad, and the Ugly. I would say this is the good guy, the next guy is the bad guy, and the ugly is this property here. Right? So, well, if we were talking classical mechanics, then we would have the Vlasov term, right? Now, since we are not talking classical mechanics, we have something which looks much more complicated, but sort of has a structural similarity. And what it is really is a pseudo-differential operator which depends on the potential and which acts on W epsilon. And actually, I don't really want to write down what this pseudo-differential operator is. I just want to tell you that the symbol of this pseudo-differential operator is a difference quotient which depends on the potential. This is the symbol. I think I times this is the symbol, yes. So what do I mean by this? Well, I mean that you get this operator or you get the Fourier transform of this operator if you take this symbol, multiply by the Fourier transform, velocity Fourier transform of W epsilon. Okay, so this operator here is nothing but the back Fourier transform of the product of the symbol and the Fourier transform. Never mind. I mean, the important information that is contained here, you see that as epsilon tends to 0, if I assume that the potential is sufficiently smooth, this term will converge to its gradient as epsilon tends to 0 times v. V after Fourier back transformation corresponds to a derivative in psi. Multiplication of v corresponds to a derivative in psi after Fourier back transformation. So formally, this should convince you that in the classical limit as epsilon tends to 0, you get back the Vlasov equation. But okay, this is just a sideline at the moment. So okay, so this is Wigner's point of view. The idea is go into phase space, define a phase space function, which we call W epsilon, is the Wigner transform of the wave function. The phase space function W epsilon has good properties corresponding to observables, and it satisfies an equation which is sort of reminiscent of the classical Vlasov equation of classical mechanics. Yeah? But it has this big drawback that it's not, in general, it's not positive. Okay, so that was Wigner's approach. Now, let me go, well, actually, this is very classical. You find, I mean, as I said, Wigner's approach was sort of not very popular in the mathematics community because of this defect of the Wigner function here, but by now it's accepted that it's a very good tool and that you can do many things with it, doing workarounds and so on. Now,
what if the epsilon goes to zero to Wigner's transform? So does it still non-negative at some point? Or
that's an important point to which I will get. Actually, what you can prove is that as epsilon tends to 0, W epsilon will converge to a positive measure. That's very important. Okay, I'll get to that. Let me go through the next basics now, which is Bohm's approach. And this is called Bohmian mechanics. And I think what we are talking now, well, I mean, Schrodinger was stuff of the 20s. Wigner was basically stuff of the 30s of the last century. And Bohmian mechanics is basically stuff of the 50s of last century. Okay, now Bohm takes a completely different approach. Bohm says, well, I want to put quantum mechanics as much as possible in a classical mechanics framework. And here he says, this is not enough for me. Okay, so what is classical mechanics? Well, in classical mechanics, I have a particle to which I associate a position and a velocity. And then I write down Newton's equations of motion for the particle. Okay, now I want to do the same thing here. Now, first of all, I have to see what is the velocity of a particle. Well, essentially, if you have the flux density, and if you have the position density, then clearly you can write the flux density as the position density multiplied by the particle velocity. Or by the mean particle velocity, if you want, and if you come from a phase space framework. Okay, so that means that given J and rho, I define the particle velocity as the quotient of this. Now, what is this in terms of the wave function? Well, in terms of the wave function, I have here the imaginary, well, I can write it as the, well, let me write it in this form, as the imaginary part of epsilon gradient psi epsilon bar divided by psi epsilon bar. Right? Because keep in mind that J epsilon is the imaginary part of epsilon, psi epsilon bar, gradient psi epsilon. Rho epsilon is psi epsilon bar. So this is basically what comes out if you want. Yeah? Now you can immediately see that there may be a mathematical problem involved, and the mathematical problem is what happens if psi epsilon hits 0 somewhere. Okay, but let's ignore this problem for the moment. Huh? Anyway, so here is my velocity, and Mr. Bohm says that, well, I'm interested in the trajectories of u epsilon. Right? Well, that's weird in some sense, isn't it? Because what he says is basically that if I have a wave function, right, which solves Schrodinger's equation, then I can write down the position density, I can write, the position density, I can write down the flux density, I can write down the velocity. Once I've written down the velocity, I can sort of as a post-processing compute the Bohmian trajectories. Yeah, I need initial data. And this is, of course, some point, say, x. Yeah. So, I mean, this is like an Eulerian formulation of quantum dynamics. Well, really, in some sense, it's only, so far it's only a definition. I have to tell you what this flux does, right? Before it has any sense. Yeah? Because so far I only said, okay, I assume I have a velocity and assume I don't have too many problems with zeros of the velocity of the wave function. That means with points where the velocity is not well defined, then I can write down this flux. Okay. Okay. I'll get to the mathematics in a moment. Just before I do that, I like to do something which in fluid dynamics is done very often, and that is I want to pass from the Eulerian formulation to the Lagrangian formulation. So I want to pass from Euler to Lagrange. Okay, what does it mean to pass from Euler to Lagrange? It basically means that I have to compute the second derivative of the position vector. I have to compute x double dot. Right? So essentially I have to compute, I introduce x dot as p. Yeah? You can refer to p as the momentum or something, assuming that mass is unity. And then I have to compute p dot. And what is p dot? Well, you see that p dot is, of course, I can compute it assuming that I know u epsilon. It will be u epsilon t plus u epsilon in gradient applied to u epsilon. Well, okay, what I want to do now is, of course, I want to close the equation, right? Okay, but how can I close the equation? Well, there is a formulation of quantum mechanics which is called quantum hydrodynamics. And quantum hydrodynamics basically says the following. Assume that your wave function psi satisfies the Schrodinger equation. Then we already know that rho epsilon satisfies this conservation law. Oops. Okay, but there is also a second equation that I can write to close the system. And that means I can write an equation for the time derivative of the flux density. Yeah? And let me tell you what the equation is, and you will sort of see that this is very reminiscent of classical fluid, of classical compressible fluid dynamics, and that is the following. And then I have plus rho epsilon times the gradient of the potential. Well, if I wrote equals 0 here now, you would recognize immediately classical compressible fluid dynamics, where the pressure is given by the gradient, is given externally by the gradient of the potential. But unfortunately, actually, that's the way it is. This term is not equal to 0, but there is a right-hand side, and the right-hand side is this one. It's a complicated term. It's the is rho epsilon times the gradient of Laplace square root of rho epsilon divided by square root of rho epsilon. Well, how do you get these equations which kind of look magic? Well, you just take the Schrodinger equation. You write in the Schrodinger equation, you write psi epsilon is equal to square root of rho epsilon e to the s epsilon divided by epsilon. Rho epsilon is, of course, the square of the absolute value of the wave function. S epsilon is the phase. Yeah, and clearly J epsilon you can compute is rho epsilon times the gradient of u epsilon. Okay, and then you put this ansatz into the Schrodinger equation, separate real and imaginary parts, and both of these equations pop up after some actually very limited algebra effort. You have to think that these equations here can be found in every book of quantum mechanics, in every good book of quantum mechanics, at most on page 15, I would say. So it's not really very deep. But it's very interesting because it tells you that quantistic flow corresponds to essentially compressible fluid equations, compressible Euler equations, subject to a regularization, which admittedly is very complicated, but still there's an epsilon square up front, which might help you in the very end. Well, there's a problem, there's a singularity here. Never mind. Okay, so how can I close this equation now? Well, clearly what I have to do is I have to rewrite this equation in terms of an equation for rho and u. Okay, but this can, of course, be done.
So is it epsilon square? Well, you have a total derivative at the right.
No, here's epsilon squared. Yeah, but this only corresponds to what, the rule that I said corresponds to wave function. Okay. Okay, now this can be written in the following way. Plus. Okay, now I have to copy the term on the right-hand side in a correct fashion. Okay, so this is the equation. This is the quantum hydrodynamic system written in terms of position density and velocity. So you see that now you can proceed here, right? So you can proceed here in the sense that you say that this is equal to minus gradient v of x plus epsilon square half gradient of Laplace square root of rho epsilon divided by square root of rho epsilon. Now let me introduce a notation. This term is actually very often referred to as the Bohm potential. Okay, but keep in mind it depends heavily on rho epsilon. Yeah? Now, okay, now what is my Lagrangian formulation of quantum mechanics? You just have to look here. The Lagrangian formulation of quantum mechanics is x dot is equal to p, and p dot is equal to, and now you recognize immediately that if I wrote only this, it would be perfectly the Newtonian equations of motion, but quantum life is not so easy. I have a remainder, and the remainder is plus epsilon square. Let me just be strict with myself and keep the notation that I have here. Sorry. Let me introduce this definition for the Bohm potential as minus epsilon square half Laplace square root of rho epsilon divided by square root of rho epsilon. So now I can write this as right. And of course I need initial data for this. Where u sub I is just the initial velocity. And now you see we have almost achieved something remarkable. Almost. And that is we almost wrote quantum mechanics without use of the Schrodinger equation. Except I've been cheating you here a bit, because you see that this Bohm potential depends on rho epsilon. And rho epsilon still comes from the Schrodinger equation. But there is a way to compute rho epsilon without the Schrodinger equation, and that is just if I know these trajectories here, all I need to do is additionally solve this equation. Oops. Right? Well, you still might say this is not completely there yet. Let me rephrase this to you. How long do I have? 2 more minutes. And at best what I do now is I give you a theorem. And this theorem was actually proven quite a while ago by Berndl et al. And other people. And this theorem is actually rather surprising. The theorem says the following. It says, first of all, if you look at this flow only, if you think of this flow as a flow map on position space, okay, then of course when you think of ordinary differential equations, there is 2 issues that you have to keep in mind. And one is the regularity of the right-hand, well, the main issue is the regularity of the right-hand side. Okay? And you see the regularity of the right-hand side has 2 impacting factors. One is, of course, the regularity of the wave function. And the other one is the occurrence of singularities here. Okay? Now, the Berndl theorem says the following. It says that assume that V and the initial wave function are C-infinity functions. then he says, or then they say, then the flow X is defined rho epsilon initial almost everywhere on Rn for all t in every compact interval minus t capital T. Okay. So I give you any compact interval minus t plus t, then the theorem says that this phase space flow here is defined, is well defined, but only almost everywhere with respect to this measure here. And this measure is just the initial position density. Well, essentially it tells you that where initially you don't have particles, you cannot define these trajectories, right? Because then if at time t equals 0 you don't have a particle, then I mean the trajectory here doesn't make sense. Huh? Still, it's a surprising theorem that you can go this far. Okay, but then it also tells you the second line, and the second line is that the theorem tells you that you can sample rho epsilon, the position density, from the flow. Precisely, you can prove that rho epsilon at time t is the push forward of the initial measure, rho epsilon I, through the flow X. Okay? Now, to write it nicely, so this, so X sub, well, this is a bad notation. Push forward rho epsilon I. Now this is maybe you're not familiar with the concept of mass transportation, but this basically tells you that you can compute the position density at time t by pushing forward the measure, the initial rho measure, through this map. Now in weak formulation, this can be written down as the integral of sigma of x times rho epsilon of x d dx is equal to the integral of sigma of capital X, which is this flow here, of x and t, integrated with respect to the initial position density, and this holds for all sigma, say, in C0 infinity, for all test functions sigma in C0 infinity. So basically, what does this theorem tell you? It tells you, well, this theorem basically tells you that you can sample, that you can compute rho epsilon at time t by just sampling, or by just by a ray tracing method from the trajectories. Okay? So, still in this formulation, you still didn't get rid completely of the Schrodinger equation. Now, do I have one more minute to finish? Okay. In order to get rid of the Schrodinger equation completely, we have to go back to the Lagrangian version. We have to go back to the Lagrangian. Well, okay. That requires some more explanation. Let's take the break now, maybe. Yeah. Okay.
Okay. Any questions? Okay, so 이제 가도 되고 12시에 여기